Okay, so we're going to talk about hypothesis tests dealing with proportions. And to get started, we're going to do a little sort of mental activity, and some of you are actually going to think this is amazing because you're going to guess the same number that I'm going to predict. But for the rest of us, this is going to be sort of a thought experiment. So I want you to write down the first number that you can think of that has the following characteristics. We're going to pick a two-digit number between 10 and 50 where both digits are odd and the digits do not repeat. Okay, everybody got a number? Okay, so let's take a second and sort of think about what possible values we have if we were to sketch out this type of distribution. What would we notice, and then what would did we expect this to sort of happen? Well, when you go through the list, there's only so many options. So 13, 15, 17, 19, 31, 35, 37, and 39. And for some reason, human nature tends to make one of the numbers come out more often than another. But in reality, if it's completely random, out of 100 people in the room, every number should have about the same number of people. So we should notice what's called a uniform distribution. And I found in doing this in face-to-face classes that it actually isn't uniform at all, that there is a particular value that jumps out. And again, we'll talk about that. And the interesting thing is, when I do this in face-to-face classes and students see their number show up more often than not, it sort of surprises them when they stop and think about, well, it really should be uniform. We should have all gotten different numbers. And so, for some reason, 37 shows up more often. And so, we're going to go through a process, that's what hypothesis tests do, of is that weird or not? Is there a reason why 37 shows up more significantly? And is that something that maybe there's some other truth going on? So again, in a group setting, I would calculate how many times each of the other numbers showed up, and then we'd calculate sort of a probability. Now, given that there's 8 choices, I would expect 37 to show up 1/8 of the time. And what we would test as a class is, does this happen more often than the 1/8? And so a hypothesis test will allow us to come to that particular conclusion that we're surprised that this number showed up more often or not. Okay, so what exactly does a hypothesis test do? It is a calculation that tells us if a sample statistic or probability p hat occurs by random chance or not, or if it's statistically significant. Okay, in other words, go out and collect data, and I'm looking to see, is the sample something that's rare enough that I think there's something more going on, or is it just random? And if my sample shows up 37% of the time, that's nothing to get too excited about. So statistically significant means it's not by random chance. We think that the sample is very rare, and we think that there's some sort of outlining purpose behind that. Okay, and so kind of graphically, again, just kind of remind us of this illustration. We think samples that occur in the middle part of the data set, very boring, nothing too shocking about that. So is our sample something that would occur somewhere in the middle, or is it something that would occur maybe in the tails? And a test statistic will allow us to calculate that and come up with an actual number, a p-value, a probability that indicates whether it's a rare occurrence or whether it's not, or at least suggesting evidence of that. Okay, so when we do a hypothesis test, we first suppose the effect is not present, and then we see if there's evidence against this. This is not new to us. We've kind of talked about murder trials more in detail. But reminder, how does a murder trial work? Well, we assume the person is innocent and try to look for evidence that they are guilty. And hypothesis tests do the same thing. Okay. Now this time we're dealing with proportions, but hypothesis tests in general are going to have the same steps. We go through assumptions, which is different for each type of data. So this is our first chance looking at proportional data and doing a hypothesis test. We make some sort of statement about what we expect to see versus what we feel is going on. Then we do some sort of calculation, and then we make some sort of conclusion. And the nice thing is these steps are actually the same as if they were for a confidence interval, so that first process isn't too new for us there. Alright, that brings us to proportional data. So we are doing assumptions for what's called a z-test. We need to, one, have some sort of confirmation, some statement, some way that there's an SRS of context. This can be stated in the problem, or it can be something that we can reasonably assume. And we will have to make a sentence saying, I thought about how we got the data and it makes sense to me that there is a randomness to it. Because we're dealing with proportions, we need to check a normality condition. So normality simply means that our sample size is large enough to show that n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10. And then we have sort of an independence condition that our population is at least 10 times larger than the sample size. So kind of give you a sense, if the sample's got 100 people in it, I need to have enough evidence, or it needs to be fairly reasonable to assume that the actual population is at least 1,000 people big. 100 times 10 gives me 1,000. If I got 350 people, then 3,500 people should be in the population, stuff like that. And these assumptions are actually the same assumptions as they are for confidence intervals. So again, not a surprise on that proportions carry over into hypothesis tests that way. Okay, so let's go through an example, and let's just check the assumptions here, and again, we'll eventually get to the calculation part on this. So we've got a countrywide water conservation campaign was conducted in a particular county. A month later, a random sample of 500 homes was selected, and water usage was recorded for each home. The county supervisor wanted to know whether the data supported the claim that fewer than 30% of the households in the county reduced water consumption after the conservation campaign. Okay, so let's talk through our assumptions. Do we see anything in the statement that talks about randomness? And right after the sentence, a month later, a random sample. Okay, so that's safe to assume. Then we need to check the normal condition. Do we see n and p? So n would be 500, p would be 30%, and so I just need to double check that np, so 500 times 30% is at least 10, and then n times 1 minus p, so n times 70% is at least bigger than 10, and they both are. And is it safe to assume that in any given county, that if I have a sample of 500 homes, then there should be at least 5,000, and that's a fairly safe connection there. So let me just put it on the screen there, the three conditions that we check through. And so part of a hypothesis test actually would be to write out these assumptions and just indicate that yes, I have considered them and I've double checked all the things, and I made a statement about each one. Okay. Next, how do we write the hypothesis statement? Okay, so we have two things we want to consider. We have a null, which is a statement about the claim being tested, and this is something regarding there's no effect or no difference. In other words, when I went out and collected data, I did it for a reason. If the data doesn't support anything interesting, then the null hypothesis would be what we started off thinking is happening. And so the symbol for that is H naught. The alternative hypothesis is the reason why we bothered to collect data in the first place. And this is a statement based on something we suspect is going on. And the symbol for that is HA. Okay. In Normal in a null hypothesis, we write our parameters equal to some hypothesized value. So for proportions, this will be some sort of percent of some kind. And then our alternative is one of three things. It's either greater than a proposed value, less than a proposed value, or just not equal to. That's what's called a two-tailed test. Okay, so going back to that class example that we started off with about whether or not we could guess 37, I would want to phrase out my hypothesis statement starting with my null, and so I expect it to be 1/8, and I want to test that it's higher than 1/8. So I would set that up where the null is equal to 1/8, the alternative is greater than 1/8, and then I have to in context define what P represents. So P is a variable representing the population, and it's the true proportion of people who answered 37. Okay, so that would be the null and alternative for this particular statement. Okay, flu vaccine claims that claims to prevent a certain type of flu in 70% of the people who are vaccinated. Is this claim too high? Okay, so let's start with what our null is. Our null would be, we expect it to be 0.7, and if I'm asking the question, is this claim too high, I am actually claiming that 70% or 0.7 is too big a number, which means I suspect it's actually smaller than that. So the null would be what's on the screen, and the alternative is less than 0.7. And again, I have to define in context what that variable means. That P is the true proportion of vaccinated people who do not get the flu. Okay, another one of these. Many older homes have electrical system that use fuses rather than circuit breakers. A manufacturer of 40A fuses wants to make sure that the mean amperage at which its fuses burn out is in fact 40. If the mean amperage is lower, customers will complain because the fuses require replacement too often. If the amperage is higher, then manufacturer might be liable for damage due to the electrical system due to fuse malfunction. So what's the hypothesis? Okay, so you got to think about what do we expect to see. We expect it to be at 40, which would be our null, and in this case there's sort of bad on either end. So if it's too small, if it's less than 40, there's a concern, and if it's too high, there's a concern. So this would be a nice classic example of that two-tailed idea. So we expect the mean to be 40 as the null, and the alternative is that it's not 40, simply because I don't really want to show evidence either way, greater than or less than, but I just want to know if it's different than 40. So, and then where the mu is the true mean amperage of fuses. Notice as we're defining these things, these variables are all in terms of population parameters. These are all p's, mu's, instead of p hats in x bars. These all variables represented by the population. Okay, so a couple of statements to remember about hypothesis statements. Hypotheses always refer in terms of populations. In other words, we use parameters, not statistics. The alternative hypothesis is what we are trying to gather evidence on, is what we are trying to prove, and we want to make sure we have some sort of statement about context, whether or not what the data represents, what the variables represent, as far as in the word problem itself.